Hello, welcome to another module in this massive open online course. So, in this module, let us look at an interesting application of Gaussian random vectors in the context of machine learning, and in particular linear algebra, linear transformations of Gaussian random vectors in the context of machine learning. Very good. So, we want to look at an interesting application, one of the first in a series of applications we are going to look at in this course, machine learning, ML, right. The particular problem that we want to look at is what is termed as classification. Classification with Gaussian classes. What the problem is essentially very simple. You have the data belonging to two classes. So, you have class A and you have the data, another set of data belong to and of course, there can also be some kind of a sparse overlap, right, because these are after all Gaussians, right. And what you are trying to do is you are trying to classify this or basically separate these into two different classes, right. So, you have class, let us call this as class 2 and let us call this as class 1. And you are basically separating these two classes, or you are basically classifying, right, the data into these two classes. So, partitioning the data into two classes, and now let us say these classes are Gaussian. Now, in this problem, and this frequently arises, these classes are Gaussian. Class 1 is Gaussian with mean mu1 bar covariance sigma. So, we are simplifying this by assuming the same covariance sigma. So, class 2 is Gaussian with mean mu bar or mu2 bar. So, the means are different. First one has mean mu1 bar, second one has mean mu2 bar, but the covariance is same. So, this is class 1, class 2. So, these two classes, both these classes are Gaussian. Now, the point is, if there is a new point, now the question is, if there is a new observation x bar, which class does x bar? The question is, which class does x bar belong to? Which class does x bar belong to? That is an interesting. For instance, let us take a simple example. You can have two classes. You can have, for instance, an image. Image can contain two classes. One class belongs to a certain object, other class of pixels belong to a certain object, right. You are trying to find a new pixel, which object does it belong to? And let's simplify it even further. Let's say there is an image with a single object. You have the object, right, which is we can term as the foreground object, or a person, that is a foreground, and then you have the background, right. So, you can think of these two classes as one being the foreground right, other being the background. This is an example, right. This can be anything. This can basically presence of an object. So, foreground, background pixels. So, foreground pixels, background pixels, foreground pixel, background. Now, we have new pixel vector x bar. Which does it belong to? X bar does belong to. Does it belong to the foreground? Does it belong to the background? In general, we are saying that these two pixels are basically distributed as Gaussians. Foreground Gaussian with mean mu1 bar, covariance matrix sigma. Background mean mu2 bar, covariance matrix sigma, right. How do you classify a new pixel x bar? Let us look at this problem. Let us now write the probability density function of the foreground. So, look at the probability density for each class. Let us look at the class 1. Let us look at class 1. What is the probability density for the class 1? P of x bar, which is basically parameterized by mu1 comma sigma. This is the multivariate Gaussian random probability density function with mean mu1 bar. In fact, I have to write mean mu1 bar. Yeah, mean mu1 bar 2 pi sigma n. This is the determinant, as you know. This is the determinant of sigma, determinant of the covariance. This is the probability density function times e raised to the power of minus half x bar minus mu1 bar transpose sigma inverse x bar minus mu1 bar. Okay. So, this is basically your PDF corresponding to. So, this is the determinant, that is what I was saying earlier. This is the determinant. Sorry, there is no n here. This is the determinant, right, minus half x bar minus mu1 bar sigma inverse x bar minus 1, and this is the Gaussian PDF. And this is now termed, in the context of classification or detection, this is termed as the likelihood corresponding to class 1, because you are looking at it as a function of the different classes. X bar is fixed. So, probability density function is basically a function of x bar. Now, we are looking at a point x bar is fixed, and you are looking at its with respect to the different classes, right, or the different hypotheses. So, therefore, this is known as the likelihood. Okay. So, this is what is known as the likelihood of class 1. This is an interesting terminology. This is the likelihood of class 1, which is nothing but the probability density function of evaluated at the point x bar corresponding to that particular class. Now, let us look at the likelihood of the class 2, which is nothing but P of x bar mu2 bar sigma. This is equal to 1 over square root of 2 pi raised to the power of n magnitude sigma, that is the determinant of the covariance matrix, times e raised to minus half x bar minus mu2 bar transpose sigma inverse x bar minus mu2 bar. Okay. Now, so this is basically what we are calling as, this is basically your likelihood, or this is basically, let me just write it with a different color, this is basically the likelihood. This is the likelihood of class 2. This is the likelihood of class 2. Now, how do we make the decision, or how do we do the classification? Now, what is the classification rule, or what is the classifier, as what we call in the machine learning, what is the classifier, or what is the classification rule? The classification rule is very intuitive. If the likelihood corresponding to class 1 is higher, choose class 1. If the likelihood corresponding to class 2 is higher, choose class 2. If both likelihoods are same, which arises with 0 probability, right, you can choose any class, right. So, if the classifier is very simple, the likelihood corresponding to class 1, if is greater than or equal to likelihood class 2. If this is the case, then choose class 1. That is your simple decision rule. Else so we can write it, if likelihood of class 1 greater than or equal to likelihood of class 2, choose class 1, else choose class 2. This is your simple classifier. That is your simple classifier. You compare the two classes. If the likelihood, that is P x bar mu bar sigma bar x bar mu 1, I am sorry, mu 1 bar sigma 1 bar greater than or equal to P x bar mu 2 bar comma sigma, sorry, this is not sigma bar, this is sigma, greater than or equal to sigma, then you choose. So I can write this both as a single statement. If this is greater than or equal to this, choose class 1, or I can write this as over the greater than, and if this is less than this, choose class 2. This is the way you write it in a compact fashion. If it is greater than or equal to the likelihood corresponding to class 2, so over the greater than or equal to symbol I am writing class 1, over the less than symbol I am writing class 2, below the less than symbol I am writing class 2. So this automatically tells you what is the classification rule. If the likelihood corresponding to class 1 is greater than or equal to likelihood corresponding to class 2, choose class 1, else naturally choose class 2. Alright. So essentially this is the simple problem, or this is the simple rule for this classification problem. So we were saying choose C1 if the likelihood corresponding to class C1, if the likelihood corresponding to C1, which is given by this is the likelihood for C1, right. So if the likelihood corresponding to C1 is greater than or equal to this likelihood corresponding to C2, and of course if it's otherwise, if it's less than or equal to the likelihood corresponding to C1 is less than likelihood corresponding to C2, then choose C2. Okay. Now let us simplify this. Let us substitute the expressions over here. So that essentially gives me choose C1 if, well, if you substitute those likelihood expressions, if you go back and take a look at it, let me write these expressions anyway. So this essentially implies that 1 over square root of 2 pi raised to the power of n magnitude or the determinant of the covariance e raised to minus half x bar minus mu 1 bar transpose sigma inverse x bar minus mu 1 bar. If this is greater than or equal to, choose C1 if this is greater than or equal to 1 over exactly identical constant, that is square root of 2 pi determinant of sigma e raised to minus half x bar minus mu 2 bar sigma inverse x bar minus mu 2 bar. And now you can see from this that these constants, these go away, and now you only are left with the exponential, and essentially you can choose C1 if this exponent on the first is larger than the quantity in the exponent on the right, but there is a negative sign in front of it. So essentially what it means is choose C1 if, and the half is essentially its scaling factor. So choose C1. So you can easily check this. C1 this reduces to choose C1 if x bar minus mu bar transpose sigma inverse x bar minus mu 1 bar, this is less than or equal to x bar minus mu 2 bar sigma inverse x bar minus mu 2 bar transpose sigma inverse x bar minus mu 2 bar. Okay, all right. And therefore, now if you simplify this further, this implies if we expand this, this will give you x bar transpose sigma inverse x bar minus 2 mu 1 bar sigma inverse 2 mu 1 bar transpose sigma inverse x bar plus mu 1 bar transpose sigma inverse mu 1 bar. This is less than or equal to again the same thing, x bar transpose sigma inverse x bar minus 2 mu 2 bar transpose sigma inverse x bar plus mu 2 bar transpose sigma inverse mu 2 bar. And now you can see the x bar transpose sigma inverse x bar, this cancels from both sides. This implies essentially that now if you simplify it, you bring this on to the right, this implies mu 2 bar minus mu 1 bar transpose sigma inverse x bar, this is less than or equal to half mu 2 bar transpose sigma inverse mu 2 bar minus half mu 1 bar transpose sigma inverse mu 1 bar, which now once again if you simplify this, this implies that it is not very difficult. After some manipulation you can show this, this is essentially mu 1 bar minus mu 2 bar transpose, not very difficult to see this, mu 1 bar minus mu 2 bar transpose sigma inverse x bar minus, well, mu 2 bar plus mu 1 bar divided by 2 greater than or equal to 0. So, choose C1 if this condition holds. If this condition holds, otherwise you choose C2, and this finally implies, I can write this conveniently as W bar transpose x bar minus x naught bar greater than or equal to 0, that is choose C1 if this holds greater than or equal to 0, else if this is less than 0 choose C2. Remember, this is how we write this condition. This is very interesting and I am going to explain more about this. I am sorry, this has to be the sigma square, sigma inverse has to be there. So, W bar transpose sigma inverse, right, sigma inverse this, and or you can, I am sorry, you can write this as W bar transpose. I think this is fine, it is better to define it this way. So, where W bar is, well, where this quantity W bar equals sigma inverse mu 1 bar minus mu 2 bar. So, W bar transpose will once again give you mu 1 bar minus mu 2 bar sigma inverse. In fact, I can write this as W bar transpose, and x naught bar, which is mu 1 bar plus mu 2 bar by 2. So, this is the condition, and you can see you will later see that this is essentially W bar transpose x bar greater than this W bar transpose x bar minus x naught bar greater than equal to 0. So, this W bar, if you look at this W bar transpose x bar equals W bar transpose x naught bar, this is actually a hyperplane, this is an n-dimensional plane. We are going to look at the set of all vectors that satisfy this is essentially a hyperplane. We are going to look at that. Okay. So, that is essentially what this is saying, and so this is the condition. So, choose C1 if W bar transpose, and this is also known as a discriminant. Now, let us come. Now, why is this very interesting? Let us look at a simplification. Let us set sigma equals, that is a capital matrix sigma equals sigma square times identity, that is considering independent identically distributed Gaussian random variables. We know that when the covariance is essentially proportional to identity, that corresponds to independent identically distributed Gaussian, that is a Gaussian random vector with independent identically distributed Gaussian random components. Okay. Now, therefore, this is essentially for IID Gaussian components. This has a very interesting, right. So, IID Gaussian components, you have your W bar becomes which is essentially W bar becomes 1 over sigma square mu 1 bar minus mu 2 bar, and your condition becomes, if you look at this 1 over sigma square times 1 over sigma square times mu 1 bar minus mu 2 bar transpose x bar minus x naught bar greater than equal to less than 0. So, choose C1 is greater than 0 equal to 0, C2 is less than 0, and of course, since there is 0 on the right, 1 over sigma square can be removed, and net you get the condition, that is choose C1 if mu 1 bar minus mu 2 bar transpose x bar minus x naught bar greater than equal to 0. I choose C1 is greater than equal to 0, C2 if it is less than 0. And realize that this x1 naught bar, this is nothing but, if you look at this x naught bar, this is equal to mu 1 bar plus mu 2 bar divided by mu 1 bar plus mu 2 bar divided by 2. This is equal to essentially the midpoint. Mu 1 bar comma mu 2 bar. This is the midpoint of these two means, that is mu 1 bar comma mu 2 bar. And therefore, the condition is something that is very interesting. If you look at these two Gaussian classes, let me just draw the picture again and show you. So, you have these two Gaussian classes, and this one has mean, you have the mean that is mu 2 bar, and you have the mean that is mu 1 bar. Now, you join these two, I am sorry, let me just write this appropriately. So, this is your mu 1 bar, and now you look at the midpoint. Okay, let us draw this hyperplane that bisects these two. So, this is the perpendicular bisector. This is the perpendicular bisector, and what you will see is that is that this is the midpoint, which is essentially mu1 bar plus mu2 bar divided by 2. Now, look at any point x naught or look at any point x bar. Now, mu1 bar minus mu2 bar is this vector, mu1 bar minus mu2 bar is basically the difference vector. So, this is your mu1 bar, this is your mu2 bar. So, mu1 bar is mu2 bar is the vector starting at mu2 bar pointing ending at mu1 bar pointing towards mu1 bar, right. Now, x bar minus mu0 bar is this vector. So, x bar minus, so now if you look at it x bar, so now if you look at it your mu1 bar minus mu2 bar transpose x bar minus x naught bar, which is the dot product between these two vectors, is greater than or equal to 0 if this angle theta lies between 0 and 90 degrees, because remember this is nothing but this is essentially equal to magnitude of mu1 minus mu2 times or norm of mu1 minus mu2 times norm of x bar minus x naught bar times cosine of theta, where cosine of theta is the angle between x bar minus x naught bar, that is the midpoint mu1 bar plus mu2 bar by 2 and mu1 bar minus mu2 bar. If this angle lies between 0 and 90, right, this is positive, which means it will be classified as C1, and you can clearly see this angle, I am sorry, I have to say this angle less than minus 90 degrees less than equal to theta less than equal to 90, that is it lies anywhere, x bar lies anywhere in this side of the hyperplane, right. So, this is greater than equal to 0 if x bar lies on side of, you can say side of mu1 bar. On the other hand, for any point here, which is your x bar is here, and now if you look at again once again this angle, the angle between mu1 bar minus mu2 bar, this angle theta, cosine theta is equal to less than 0 for 90 for theta which is greater than 90 degrees or theta less than minus 90 degrees, right. So, you can say theta greater than 90 degrees. So, theta less than minus 90 degrees, and when cosine theta, and when this cosine theta is negative, then for all points on this side of the hyperplane you will have mu1 bar minus mu2 bar transpose x bar minus x naught bar, this will be essentially less than 0. So, essentially if you look at this, let me just draw this figure again. You have mu1 bar this is the midpoint, this is the perpendicular bisector. So, this entire region, so this is your mu1 bar, this is your mu2 bar. So, this entire half space we can call it, in fact this is known as a half space, this entire half space is classified as this entire half space is classified as basically class 1, right. And if you look at this side of the half space, correct, this half space, this is classified class 2. That is, if it lies on the side of the perpendicular bisector, right, that is you take them two means mu1 bar mu2 bar, draw the perpendicular bisector. If the point x bar lies on the side of mu1 bar, right. If the observation x1 bar lies on the side of mu1 bar, it is classified as belonging to class 1. If the observation x bar lies on the side of x2 bar, it is classified as belonging to class 2. Alright. So, that is the interesting, and this is very intuitive. So, it says essentially that you are classifying as belonging to the class corresponding to the mean which is closest to the observation vector x bar. That is, if you have x bar, right, if you have any point x bar, you look at the distance between x bar and each of the means, right. So, this is x bar minus mu2 bar, and this is x bar norm of x bar minus mu1 bar. And essentially what you are doing is, if norm of x bar minus mu1 bar is less than or equal to norm of x bar minus mu2 bar, then you are choosing class C1, else you are choosing C2. So, this is also essentially known as the minimum distance classifier. So, this is a very interesting thing. So, with Gaussian, covariance proportional to identity, both covariances are equal, both covariances of both the classes are equal and proportional to identity. This essentially reduces to minimum distance classifier, right. That is, basically you draw the perpendicular bisector between the two means. If it is on the side of the new observation x bar is on the side of mu1 bar, that is, it is closer to mu1 bar, then mu2 bar, classify it as class 1. If it is on the side of mu2 bar, that is, if it is closer to mu2 bar than it is to mu1 bar, classify it as belonging to class 2. So, this is a very interesting and a very simple classifier and a very interesting application of the principles of linear algebra. It combines a lot of principles, as you can see, combines the principles of the multivariate Gaussian probability density function, the covariance of a Gaussian when the components are independent, identically distributed, and finally this notion of these likelihoods and comparing the likelihoods belonging to both the classes. If the likelihood corresponding to class 1 is greater than likelihood corresponding to class 2, choose class 1, else choose class 2, and once you simplify it, you will see that it reduces to something that is very intuitive and interesting as well as intuitive, that is nothing but the minimum distance classifier, right. Basically, the half space that is closer to mu1 bar is classified as class 1, half space that is closer to mu2 bar is classified as belonging to class 2, alright. So, this is a very interesting application of linear algebra that we have studied so far in the context of machine learning, and thus it can be used to build very sophisticated machine learning algorithms. Alright. So, let us stop here, we will continue this discussion in the subsequent module. Thank you very much.